So in the last lecture we discussed about the equation of motion what we derived for a single leg articular tower. This was the equation of motion what we got, and we wanted to find out the variables in this like beta of t, k, nu t, etc. And we wanted to show that I naught, etc. We want to show that how they are all functions of the displacement. Therefore we will use a specific methodology to solve this equation of motion to find out these variables, and then we will substitute back and find out the values of theta, which is the displacement coordinate in this case, where in this case we already said this mass moment of inertia represented the damping term because it is velocity proportional viscous damping, and it's got two terms. One is the initial stiffness and one is the variable stiffness because of the buoyancy effect in the system, and f of t is of course the moments of all the forces acting upon the system about this particular point, which is the hinge from with respect to which all measurements are actually calculated in this specific case. So we also tried to find out what is the overturning moment and restoring moment, which happened in the last case, based on which we discussed and derived the value of k. So let us rewrite that equation. We already said that overturning moment, which is responsible for overturning the platform, is again the summation of SKWK, whereas the restoring moment, which is depending upon the recentering capacity of the platform, depends upon the submerged volume, which is rho Wg, summation k equals 1 to n small n of SKVK, where capital N is the number of segments considered in the analysis, whereas small n is the number of immersed segments, or we can say submerged segments considered in the analysis. Therefore we should say the resisting moment or the resisting force, actually the restoring component minus the overturning component, which was rho Wg sin theta summation of k equals 1 to small n SKVK minus sin theta summation of k equals 1 to capital N of SKWK. We also know that the restoring component of the resisting force of this system will again depend on the initial stiffness. So I should say this should be equal to k of 1 plus nu of t of theta So equating these two, we know for small angles of theta sin theta will be equal to theta itself. Using this relationship, we already said that rho Wg summation of k equals 1 to small n SKVK minus summation of k equals 1 to capital N SKWK should be equal to capital K of 1 plus nu of t. Since I am using this k as an initial stiffness, which is an undisplaced portion or unaltered portion of the platform, I am trying to alter this equation slightly. I am not going to alter anything on the total weight of the platform, but I will alter this as n naught, where n naught is the number of segments submerged at undisplaced portion of the platform. Now one may ask you a question, why we are taking undisplaced portion, because k is actually the initial stiffness of the platform, therefore we are considering this as an undisplaced portion. The moment I say undisplaced portion, obviously we all know that RT will be set to 0 automatically, because RT is an invoked stiffness additional of the spring in case of, or the Hinger joint in case when the platform is displaced, therefore that will set to 0, k will directly become the value here, which can be given by this equation, as we can call this as equation, maybe I do not know the real number, may say this is 1 2, and we can call this as 3, now I can call this as 4, where I say k is given by rho wg summation k equals 1 to n naught of skvk minus summation small k equals 1 to n skwk. This is, let us say, 4a. So, I have got one summation which is displacement, which is the function of n naught, and n naught is actually a function of displacement. It will govern how many n numbers will be immersed or submerged in the platform at any given point of time. Now, at any instant of time, nu of t, this value, initially it is set to 0 because it is undisplaced position, but any instant of time it will not be 0. So, nu of t can be given by RT. I think we are calling this as restoring force RT. K theta minus 1, same from the equation here. Equation 5. In this equation 5 we already know k, because k is calculated depending upon what is your undisplaced position configuration, and RT actually depends on what are the submerged volume elements and what is the total element given here, because W of every element is known to me. Sk is actually length of the element measured at k distance from here from the original equation. So, I know RT, I know k. So, for every theta of iteration I will know RT. Therefore, I can say that RT or nu of t is a function of k is a function of displacement again. Okay. So, already we said that k is a function of displacement indirectly, because this will be governed by the number of submerged elements in an undisplaced position. So, it is a function of displacement indirectly. Nu of t, which is again a function of initial stiffness, is again a displacement function. So, we are trying to now find out what are those variables in the given equation of motion which are all now converging to be functions of displacements. So, if I solve this equation of motion, actually which I wanted to solve is a displacement. So, I will be able to solve all these values, substitute them back, I will get the whole equation and displacement function, I will iterate them and solve and try to get for every time interval t delta t and so on. So, k is one and r of t is the next one. Now, let us try to find out what is the moment of inertia part of it. Now, let us say the mass moment of inertia of the tower the moment I say mass moment of inertia, it is second moment of area. So, I should say about the hinge, because I must always say about which point we are taking the second moment of area, about the hinge at any instant of time t. Is given by so, I want to find at any instant of time t what is the mass moment of inertia. So, summation of k equals 1 to n, where k is a count which is running for the number of segments in the given problem. I should say sk square, because I am taking the second moment of area and sk is this distance. Of course, I am looking for mass, therefore, Wk by g plus rho W, that is density of sea water, summation of k equals 1 to n star n 0 star, I will explain what it is, Cm minus 1 of Sk square of Vk. One can easily understand a catch here, whenever I am running Vk iteration I will always use small n, wherever I am running Wk or Wk by j, I mean Wk by g, mass iteration will always run on capital N, because that is the total mass of the system, whereas this is a submerged volume. Now N0 we already know that N0 is the number of elements submerged in undisplaced position. Capital N is the total number of segments in a given system, based on which you work out the weight of the platform, whereas N0 star is the number of submerged elements at any instant of time. So one can see simply a hierarchy like this: N0 less than N0 star less than N, that is the hierarchy actually. N0 is actually the value where there is no submersion, I mean there is no displacement taking place. N is of course the total number of segments, and N0 star can be at any instant of time, you know what is the number of submerged elements, and that will govern my total mass moment of inertia about the point, about the hinge, because it is on Sk into Sk square. So that is the distance of the point from the tower at the base. Now we know in the equation of motion this should be actually equal to I0 of 1 plus beta t, is it not? This should be equal to that. That is the participating term from inertia. So let me say this equation is equation number, let us say call this as equation number 6, I can call this equation number 7. So I should say IT at any instant of time should be equal to I naught. And I naught, which is the moment of inertia of the system at the undisplaced position, because beta of t will take care of the displaced portion of additional mass moment of inertia. So I naught should give you the mass moment of inertia at the undisplaced position, which can be again given by the same equation with a small variation: k equals 1 to n Sk square Wk by g plus rho W k equals 1. Now I will use N0 because I am talking about undisplaced position, Sk square Vk and Cm minus 1. Okay, let me do it in the same order. Let us say Cm minus 1 Sk square Vk. So the only difference between equation 8 and that of equation 6 is that the second part, which is caused because of the submerged effect, is only at any instant of time, but this is at the initial position of the system. That is the only difference. And we all certainly agree that IT will be definitely more than I0 by a factor of V plus T. Okay, that is very, very important, because this is what is contributing the displacement. And we all know that the number of segments submerged will be more than N naught and will be less than total N, because total N is the total number of segments available in the system. I know IT, I know I naught, equating 6 and 7 I can easily find beta t. Okay, so beta t, hence I total or IT divided by I naught minus 1. I will call equation number 9. You can obviously see here that IT and I0, which are all dependent, which are the governing factors of calculating Bt, will be actually dependent on N naughts or N naught star, which will again a function of displacement indirectly. Because if the platform is not rotating or the tower is not rotating, there is no displacement, then N0 N will be equal to N. Okay? When they are rotating, they will be keep on changing. It means indirectly this value or this factor will be dependent on the rotation offered to the system by the lateral force. So they are displacement dependent again. Okay? And this count is nothing to do with the stiffness, this is actually the count which runs only to count the number of segments in the given tower. Okay? That is why it is small k, and wherever we have got stiffness, I think we have used capital K. Okay? So we have the equation of motion, we have got the variables in the equation of motion, and we have seen that all the variables like k, nu t, beta of t, nRT, which are all functions of the displacement. Therefore, the whole equation of motion now has got only one variable, which is either the displacement or the derivative of the displacement, or velocity and acceleration. So, we must have a scheme to solve. One can ask me scheme, why I need a scheme to solve this, why can't I directly solve this. Let us look back again the equation of motion. Let us say I naught 1 plus beta t of theta double naught plus 2 zeta omega c theta dot plus k of 1 plus nu of t of theta is, let us say, the moment of all the lateral forces acting on nth segment, taking moment about the point where we are also taking moment about all the places where it is nothing but the hinge of the tower. Okay. I rewrite this, I say I 0 theta double naught plus 2 zeta omega c theta dot plus k theta. It is a classical equation of motion in theta. 2 zeta omega, please make a correction here, it is I naught, is it not? Am I right? So, it is a classical equation of motion where the remaining terms are taken to the right hand side, which of course Ft minus, let us say, I naught beta of t minus, this is theta double dot minus k nu of t. Now, look at this equation, it is a very, there is a strange characteristic of this equation. One, the left hand side of this equation is a classical equation of motion for a multi-degree freedom system, provided theta is the size of the vector. Okay. In this case, it is only one, because only one rotation is being assumed. If you look at the right hand side of the equation of motion, there are functions like beta t, k, nu of t, etc., which are all function of theta itself. So, I have a very strong coupling between the left hand side and right hand side of equation of motion. Okay, and that coupling variable is nothing but theta, which is actually the unknown of the system. Okay. Now, when you have got an equation where the left hand side and right hand side both depends on the variable itself, which is to be determined from the equation, you have to have an iterative procedure. Okay. You have to assume a value and keep on substituting and try to find whether the assumed value and the obtained value are matching. So, you need an iterative scheme. We need iterative procedure. Okay. We will talk about the procedure later. I will show you the solution now, then we will talk about the algorithm later, because I want to discuss the algorithm for all the problems at the end being common. Now, let us look back what is the mathematical model we have here, what are the assumptions we made, and then how it has been solved from the research paper directly. So, when you attempt to solve this articular tower, let us say the assumptions made in the mathematical model are the following. The fluxural deformations of the tower are negligible compared to its displacement as a rigid body. So, the tower can also have a displacement, okay, but they are negligible, they are neglected from in the analysis. The tower is ideal as a single column. If you have got multi legs, then you have got to do it separately. In this case, a single column undergoing motion only in the plane of fluid, there is no transverse vibration of the tower, that is an idealization in this case. Okay. Thirdly, the base of the tower is thoroughly hinged, it does not offer any resistance to rotation. Tower is discretized into n number of segments for our calculation purpose, and it is assumed that at n number of segments the mass is lumped at appropriate nodes. Okay, that is how the n counter is running. Once we have these assumptions made, we have the classical equation which is tallying with what we have on the blackboard here, I plus beta t theta double dot, I naught omega theta dot and k nu t f of t, where f of t is the moment of the forces acting on the nth segments on the tower about the hinge of the problem. Now, the right hand side of the screen shows you a real time problem, because it is an idealized model what you see in the left hand side. So, geometric dimensions are given there, seabed 275 meter high, the buoyancy chamber is 70 meter, 5 meter with the still water level, then 50 meter above there is a top side. The idealized system is what you see in the left hand side on the screen, whereas the right hand side is a real life system which is an ALP, anchoring leg platform, which is you can see the tanker, the shuttle tanker is used to be anchored with the tower. Okay. So, they are not actually production platforms, they are not exploratory platforms also, but they are part of production system because the shuttle tankers are used actually to transport the explode oil from a TLP or from any production unit to that of the off course for processing. So, you need to have to hold the tower or the tanker for some time when it is being shuttling out. Okay. So, this is nothing but an anchoring system. Now, you cannot have an anchoring system so rigid because the tower will have the shuttle tankers are of a very high volume, okay, and they will be subjected to a lot of motion. So, they should be arrested. So, this is one. The second thing is, if you really wanted to attempt to repair a shuttle tanker or inspect a tanker, you need to hold it in position. DPS will not work, okay. It gives lot of, it should be more or less held down in position. So, this system can also be used as one of the repair capacity to hold down the shuttle tanker for some time in the sea, because the shuttle tanker cannot be sailed back to the coast because it is unfit to sail. Okay. You need to visit the electromechanical complications of the system, you need to hold the tower or hold the tanker for some time. So, you need to have an anchoring system. Thirdly, if you really want to have a temporary naval base somewhere, you want to have a naval base temporary, maybe for inspection, maybe for some recording purposes, or maybe for some continuous monitoring in a specific location. You actually cannot have a tanker or a vessel. Of course, you cannot do it in a submerged vessel because there are limitations. Of course, the submarines can also be used for detection, but they have limitations. So, shuttle tanker of this order, a single leg tower, can be used for inspections also. So, there are many applications in naval architecture and ocean engineering as far as ATs are concerned, but ATs are never used as production platforms. They can use a storage platform because there is a big buoyancy chamber available here. You can partly store it in the buoyancy chamber itself, and remaining you can keep on pumping out to the shuttle tanker, and shuttle tanker will carry the pumped oil back to the coast for processing or regasification, etc. Okay. So, there is an example structure. You have a real time structure on the right hand side. The equation of motion already we have derived, and we have also shown the variables. We have seen that all the variables are displacement dependent. In this case, the degree of freedom is theta, which is the rotation of the tower at the hinge or respect to the hinge. If you look at the real time data of the original ALP, this is the problem which has been considered. Height of the deck is 400 meters, the structure weight is about 200 kilonewton per meter, and the deck weight or the top side is about 25,000 kilonewton or 2,500 tons. This is relatively a big value. The buoyancy chamber dimensions are available to you. The data has been borrowed from the paper. The results are also projected back to you from the paper. So, I am now discussing the results directly from the research paper, which I am quoting at the bottom here. So, the procedure what they have followed is what I will discuss later, but I will now show you the results directly, which are taken from the paper directly. So, input spectrum is the power spectral density function, which has been used with and without the pressure drag as shown on the left hand side. The response spectra is characterized by a single peak. You can see this is a single peak at a frequency of about 0.06 radians per second. It occurs at a peak energy frequency of the wind velocity spectrum, because the wind velocity spectrum has a frequency closer to this value. You will see that with and without pressure drag they have plotted, one is a solid line, one is a dotted line. This is a solid line, this is a dotted line. So, the inference says from the paper that there is no significant difference caused by including the non-linear pressure drag term in the analysis. Okay, the solution has been done with both the cases, linearization of drag and non-linearization of drag, both they have done, and they have shown that there is not much difference. The reason is they have attributed this reason to the system is too flexible. Okay, the tower is too flexible or compliance in nature. So, in case of compliant systems, drag linearization is not important. That is what we can infer directly from this kind of study. One can also see what is the effect of instantaneous position of the platform. For example, you have the platform but standing vertical, the load is applied, the platform is not vertical, but some theta is introduced because of the non recentering capability of the hinge, because initially the hinge may be able to bring it back to normal, but after n number of years the hinge will not be in a position to bring back the tower normal vertical So, if you consider the instantaneous position effect also in the analysis, it shows us the effect of instantaneous position does not influence significantly the response, because the response does not vary much. So, there are two variations noted here, one is the peak difference, one is the frequency shift. Practically there is no frequency shift at all, it does not affect the frequency content of the result. It of course affects the peak formation, but the variation is not significant. That is what the researchers reported. Therefore, effect of nonlinearities does not influence the response significantly. One can use spectral analysis. The moment you go to spectral analysis, there is always a static component coming into play here. But of course, the nonlinear hydrodynamic terms need to be linearized, because that is for the requirement of comparison. The system has shown three nonlinearities. One is the velocity squared term in the wing drag force, the other is the large displacement nonlinearity, the third one is of course the nonlinearity in the drag term itself in hydrodynamics part. They do not influence the response significantly, because the system remains too flexible to report these kind of differences. So, that is what the results and conclusion what we have in terms of instantaneous position effect of the platform and the nonlinearity present in the hydrodynamic term as well as in the wind term also. Okay. We please recollect that the wind velocity spectrum also has a nonlinear term as given by Emil Simius spectrum, which we had discussed in the earlier module. So, there are two nonlinearities coming into play here, because one is called as a static component, is called the gust component. So, there is a nonlinearity term there also, which we also say that aerodynamic admittance function can convert that term into equivalent static term, which generally the design people use in the design offices. So, there are two nonlinearities, one comes from the wind load, one comes from the wave load. So, both have been reported by the researchers saying that they do not significantly influence, does not mean that you do not have to consider, but does not influence as far as this platform is concerned, because they say that when the system remains compliant, these effects are not dominant in the response. Now, question comes that how ATs have been moved up in the analysis or the dynamic perspective to improve the functionality. So, people started having multi-legged articular towers. We have now seen a single tower, people have used multi-legs, because people have said that if you use multi-legs, then one can have more advantages. Let us see what are those advantages. So, extension of the concept of single leg led to the development of new type of platforms in early 80s with several columns that are kept parallel. Okay. Then we call this as MLAT or multi-legged articular towers. Columns are then connected to the deck and the foundation both using joints what they specify as universal joints. Universal joints are nothing but hinged connections, which of course offer no rotation restraint, but in due course of time they will also have rotation restraint, okay, because of the rusting effect or because of the loading effect. You have a hinge, for example, I have a ball, let us say I have a ball, I place the ball between the rollers. Imagine a globe, you must have seen a globe. The globe has got an arm and the globe is placed between the arm with two balls, that is why the globe will rotate smoothly. Okay. So, imagine a similar system like this. So, for a small rotation of the globe, you will see theta is varying, theta is where the inclination is being given for the globe. So, m theta curve can be plotted, m theta curve can be plotted for small rotation, for small moment, even for small moment theta can be very large. Okay. But when you apply a load to the globe, maybe you stand on the globe for example and try to rotate, you will see that it will offer some restraint. It means when m is also connected to p and then you try to find out theta, then it is a problem. So, when you have a hinge where the deck is connected and the deck is having 25,000 ton loads, obviously the m phi characteristics of the hinge or the universal joint will be now compromised. Okay. That is a very simple idea to understand how the axial load will influence the rotational capacity of the hinge. Okay. So, it will offer some constraint because of the load coming on the system. Load cannot be removed off because payload is there on the deck. So, use of universal joints ensure that the column remains parallel to one another. I will show you a very interesting, a very good video which we have taken during the experiment of MLAT. So, I will show you some experimental results on MLAT, some analytical studies on MLAT, where you will see that 4 legs are connected to the universal joint to the deck. When you apply a lateral load in terms of wave, you will see that the legs will have an articulation effect, but the deck will remain horizontal. Okay, that becomes very important because if the deck is remaining horizontal, your topside activities can comfortably take place. Okay, that is an advantage. This does not happen in single leg. I think you will have a very interesting correlation. A single leg system will have or will lose stability even for a small shift of center of gravity or buoyancy. Whereas if you got at least 3 legs in a given system, at least 3, not 4, 4 is redundant by one number. If you have at least 3, the CG will be playing between the 3 of them, therefore the stability is enhanced. It is a very simple mechanics. Okay. So people have used this idea to improve upon the design concept from a single leg tower to multi leg tower. Okay. That is why MLAT came into play, right. So they kept the columns parallel and they called this as multi leg articular towers. Articulation is a term picked up from the universal joint. Interestingly, when these towers are connected between the leg and the foundation, the deck and the leg between the universal joints, they offer no movement to the deck, therefore the yaw motion is completely compromised. I mean, there is no yaw motion on the deck at all. Okay. Yaw motion is one of the precarious motion which is undesirable in any point of view, maybe even a ship or maybe in a platform, because yaw motion will always cause the shift or swing of the center of gravity and buoyancy center, and that will create an additional load which will impose a moment on the system automatically. Okay. So that is not required to happen, therefore yaw motions are completely absorbed by the joints. Of course, the joints will have to be replaced at periodic intervals if you really want it, because the joints may become rigid completely after some period of time. So MLAT have also enhanced payloads. Earlier example we saw what Jain and Datta studied is about 2500 tons, it is 25,000 kilonewton, 2500 tons. In this case they have, I will show you, it can be much more than that, about 30-40% more than this. So payload can increase and the deck area therefore can become larger compared to that of single legs, and now you can have more production facilities here. So this platform can be also now used for production facilities. Earlier ATs were used only for anchoring facilities, inspection facilities or repair facilities or storage facilities. Now here can also become a production platform or can be a supporting system to a TLP. Okay, you can put a drilling derrick on this and try to, because why you can use a derrick, because it has got more stability. In sense the top side motion in terms of yaw is completely nullified by using an universal joint. So you can have a production facility on the top here. More and most interestingly is that since you are connecting the tower to the seabed using an universal joint, the bending moments in these joints are practically 0. So the design of the foundation of the system becomes simpler, whereas in earlier cases the design of foundation becomes very severe and very difficult. Okay, pull out etc. But in this case foundation becomes very easy, because the moment at the joint at the seabed is practically 0, because we all know that moment, bending moment at the hinged connection is practically close to 0. But there will be some moment, okay, as I showed you in M5 curve there will be some moment, but that is an initial value, otherwise it is actually practically 0 for the design considerations. That is one advantage. And more interestingly, the natural frequency of this platform has been studied in such a way that they behave much lower than the dynamic confusion factor. Okay, they do not amplify the effect, that has been studied. I will show you some results later. So some of these merits have been understood while people conceptualized multi-leg towers vis-a-vis single leg towers. Okay, that is how the dynamic analysis progressively happened from single tower to multi-leg towers. And we all know that ATs are complaint offshore type structures which are proved to be economically attractive for medium depth water depths compared to fixed type, because we started from fixed type. They can be used as loading and mooring terminals, temporary naval base. The examples, classical applications are Fulmar offshore field, Santa Barbara channel. It is best suitable for permanently mooring tankers in deep waters. Even today they have been used. They have been commonly used most importantly for rise up support systems. FMC Corporation Chicago, Illinois, Drillman Corporation Houston have been also proven to use this successfully for many years in Gulf of Mexico. ATs are used as production platforms also up to a depth of 400 meters. You can see evidences from Butt et al. In 1984. But the difficulty with this is they showed higher responses because of topside increment in the activities during production. So then Butt et al. 1984 indicated that the response control becomes an important factor. If you really wanted to use MLAT as a production platform. Okay, that was hinted in 1984. So, early 90s people thought that I have to now work on a system where I can use MLAT for medium water depths up to let us say 600 meters, because 400 people have tested, it is existing. Up to 600 meters I can use. So, I can maneuver the platform easily from that of fixed to 200 meters to that of a 600 meter, very simple foundation, easy installation, better stability and enhanced deck area, more payload in terms of production facility, but it has shown larger responses. So, people said, can I work now on response control, can I control the response now, okay, because it is giving larger responses. So, the reason was the rotation permissible at the column became higher. Okay. The structural response therefore increased tremendously because of the rotation in combination of wave, wind and currents. And when you are using this as a combination of a tanker with articulate towers, they showed complex and high responses under large wave heights, because now the moment you start using as a production platform, they will be used for larger wave heights as well. Okay. So, when you go for larger wave heights or greater water depths, they showed higher responses. Therefore, motion control became a significant concept in early 90s for offshore structures, when people desired to continue with the MLAT as one of the suitable alternative for medium water depths for exploration and production. Okay. So, ATs ensure better structural performance. Sarah and Marano said in 2010 they have shown they have got better structural performance. Of course, you have got to make few structural modifications in the existing design, and Sellers and Nedvisky 1992 showed that the capacity to encounter environmental loads are higher when you make some changes in the design in the platform. So, design conceptualization was improved by making certain suggestions as suggested by the researchers in 2010, 1992 as you see from here, but all of them including Butt et al. 1984 hinted that the response control must be attempted or must be addressed, because the response are becoming higher. And Jay in 1984 also said that the flexible risers and articulated storage system showed necessity of motion control, because they have used this as a study, because when they have an impact from the tankers they invoke larger responses again, therefore, motion response is to be controlled. And Woodard et al. 1992 also showed that the considerable reduction in horizontal displacement will enable larger deck area now. So, if you are able to control the response, then you can have furthermore larger area of the deck, that is in 1992 people hinted this. Therefore, many researches recently happened and focused saying that the response control should be attempted for better performance of the platform from single to multi-legged. Now, there is one more concept available in the literature called multi-hinge articulate towers. Instead of having hinge only at the bottom and the top, you can also have hinge at the center. One can ask me a question, what is the advantage of having more hinges? What is the advantage of having more hinges? The advantage of having more hinges is, the moment you have hinges, all these places the design moments will practically become 0. Okay. You can have a very classical example of this, a comparison of this very quickly. What is the advantage design wise to have more hinges? The point is that, let us answer this slightly later, but let us see what is the advantage first physically. Now, I give a physical example of this in terms of sports. Let us say we will take one sport which is called pole vault. I think you have used a pole vault, or you may be a sportsman. Pole vault is nothing but you have a scheme, of course a frame, and of course this is a slotted, let us say column, there is nothing but a bar, and here there will be always a pit which a person will carry a stick. The stick will have a rigid bottom, the stick will be very long, okay. So, longer than of course the height of the human being, proportionately it will be like this, it will be very long. You have to hold it at 1/3 height, where you can produce height, you can run with a good velocity, good speed, come and punch this bottom here, as the stick bends it will throw you across the rod. It is a very interesting game, okay. It is pole vault, you must have seen. People use this philosophy to actually cross the boundary walls at different locations. In villages very common, people use this. Now, I compare this, now this is the exact model of what you have as an AT, because there is no hinge in between and there is no foundation required, it is very light in system. If I introduce a hinge in between, you will see that the rigidity will be lost. Okay. Now the comparison of this is nothing but the chain which is used by Bruce Lee. If you look at the chain used by Bruce Lee, he has never used a single stick actually. He has used a chain with multi hinges. The moment you have multi hinges, you can make the chain straight, you can disconnect the chain to be not to become straight, can become segmental also. Okay. Now the moments at these points in design perspective will become 0. So you can devise or design the system not as a single member but as pieces of members, therefore the section dimensions will become very small for the same load applied on the system. Okay. So multi hinges will have advantages and demerits. Okay. Multi hinges cannot sustain lateral loads, but multi hinges on the given load can design the system to be more economical. So there are multi hinge towers also. Okay. What I am talking about is not multi hinge tower, I am talking about multi leg tower. Okay. I have legs parallel. Okay. Now once we agree that yes, response control becomes an important factor to control the responses, then Chakravarti 1987 pointed out that the deck ensures comfortable operability when you control the response even in rough sea state, and then people have used this tuned mass damper concept in the buildings, not in offshore structures, but of course Fujino and Abe attempted this, a new concept in offshore structure, and proposed this that can be used. So I should have a mass tuned for a specific frequency which should be attached to secondary mass system to the primary system to tune the response of the primary system. So Kirk and Jain 1977 attempted this and showed that the whirling motion which are complicated in nature can be also controlled, which will have a large or probability of failure of the articulate joints, can be controlled if you have the response control. Thomson 83, 84 and L1 83 showed that the complexities developed in this kind of motion is chaotic in nature, will challenge the stability of the platform. So now what we see in the picture is a multi hinge articulate tower, same single leg multi hinge. So we start with the multi hinge, we will show the multi leg platform and we will talk about response control. So we will discuss the equation of motion derivation for multi hinge tower, gradually we will move on to multi leg tower, and then we will talk about response control and MLAT itself in the successive lectures. Okay, the idea is that yes, now we are conceptually moving in the design perspective from fixed platforms to that of semi compliant systems where we studied AT, we know how to analyze them provided I give you the algorithm, and we already know how to derive the equation of motion, the variables in the equation of motion. We will move on to the progressive design development in ATs to that of MLATs and response control, where we derive the equation of motion again here. I will show you what are the complexities when you talk about response control using TMD in MLAT. Once this is agreed, then people moved on from 6 cm water depth to 1000 meter water depth, where this system was not operable, then people went to tensionless platforms. They wanted to make it completely buoyant. Now this is semi buoyant because only the buoyancy chamber is there, other the tower is attached to the seabed using a hinge joint. Now they wanted to completely offload the system, so that becomes TLP and spar etc. So we will move on to that conceptualization later. Then subsequently people use this idea in the recent past, maybe 3 years down the line, maybe in 2011-12, the same hinge was introduced back again and people started designing buoyant leg structures. So we talk about BLS or triceratops etc. So the conceptual development in terms of design along with the dynamic analysis moved from fixed platforms where we started in the last couple of lectures back to that of advanced to even regasification plants where the whole system is said to be afloating. The concept started from there. So that is how we have to understand how the design and dynamic analysis went along together parallel in the discussion in structural domain of offshore structures. So that is what we will focus in this particular module. We will take down to, once we understand this applications complete in this module, the next module will talk about the advancements in dynamics, where we talk about stochastic dynamics and how we can use this for advanced research. We will talk about that. So that is how we will end the course shortly. So we have discussed in this lecture about the equation of motion variables in a single leg AT or simply AT. We have also seen what is the physical understanding of this AT, because if you have a system, structural system, see the most important thing in offshore structural analysis and design is that you must visualize the system in practice, because in buildings you can always visualize. Okay. because you know some relative frames etc., you can always see them very quickly, whereas offshore structures cannot be seen in physical means, because you cannot either off the coast you will not be able to go there and see, and we all agree and we should know that you cannot simply visit a platform just like that. You need a permission. In fact, you have to undergo a specific class C training in helicopter to actually visit a platform. It is very difficult, you cannot simply fly, even if you are CEO of the company, if you do not have that class C training you cannot fly to the platform and inspect the platform, it is very difficult. You can only see in the photographs. Okay. So, when you can see in the photograph, which is very rare, you will not be able to conceptualize the platform in idea physical terms. Therefore, designing and analysis will become a concept only. That is why in this lecture I have given a real time comparison, how an AT is actually really existing, where does it exist, how an MLT AT really exists and what people have studied. So, I want you to read those papers back again before you really want to capture how the design and dynamic analysis got modified in terms of improvement in the design itself for accommodating the same platform with small variables in the design like introducing hinges, introducing legs etc., and how people took the design forward and then how they did the dynamic analysis. You have to understand this. If you do not understand the path of this growth or progression of this growth, it will be very difficult, the whole exercise will remain ideal in your mind, that it will become a concept. So, with that concept we will not be able to design a new platform at all. One may ask me a question, why I am interested in designing a new platform. You see, people thought about the new geometry, that is why we are getting more and more platforms in deep waters. If people remain their idea only with fixed type platforms, possibly there would have been no oil and gas exploration at this present day. Okay. So, people are constantly continuously exploring for deeper and ultra deep waters for gas and shale gas and oil exploration, because oil has become an indispensable requirement of mankind all over the world. Therefore, it has become a dictating economy factor for any country, developed, developing etc. So, even your small contribution in terms of research or idea conceptualization or even analysis methodology will definitely help this community in a larger front. Therefore, it is important that we must understand the concepts thoroughly, physical relationship of these concepts before we proceed further and think down the line individually, independently, and come out with a conceptual design which will be useful for this domain of research and production in any country wherever you are. Thank you.